Today's lesson is going to be an introduction to plate tectonic theory and evidence for plate tectonics. We're going to start out by getting into a little bit of history because it's important to explain how the ideas of plate tectonics developed. The story starts with Alfred Wegener in the early 1900s. At this time, Alfred Wegener was hypothesizing that all the continents were once joined together in a single landmass that he chose to call Pangaea, which is Greek for all land. He proposed that Pangaea, over time, had split apart and that the continents had gradually moved to where they are now. This process, for a time, became known as continental drift. So far in the story, the idea of plate tectonics is not quite developed yet. Alfred Wegener has put the first kind of thoughts into the idea that the continents may have moved over time, and the earliest incarnation of this idea comes to be known as continental drift. Alright, so like we were saying, according to the hypothesis of continental drift, all the land on Earth was once part of one gigantic landmass, which Wegener named Pangaea, meaning all land, and that over time the continents, or this one landmass, broke into the continents, and that the continents slowly drifted to where they are at present day. Alright, so this picture depicts Pangaea about 200 million years ago, before it began breaking up. Wegener called the southern portion of Pangaea Gondwana and the northern portion Laurasia. Alright, let's go forward in time some. And here are the continents about 70 million years ago. You can see that Pangaea has now broken up, and this has started to cause the Atlantic Ocean to form, and also this area here called the Tethys Sea. Alright, you can notice that India has not yet drifted up and collided with Eurasia yet, but in time it will do this to form the Himalayan mountains. India will become part of the larger continent of Asia, and its collision with the Asian continent will force the Himalayan mountains upward. Alright, now here are the continents as they are positioned today. They're still moving, but it's very, very slowly, and they've always moved very slowly, at about the speed your fingernails grow, or they say, roughly, a couple inches every year. Satellite measurements confirm this movement, and it's interesting to note that the Atlantic Ocean actually gets a few inches wider every year. So North America and South America every year get a couple inches further from Europe and Africa. All right, that might not seem very significant in the short term, but if you think over the course of millions of years how much, those inches add up, how much distance that ends up adding up to over that vast period of time, you can see how the continents can go from, one position to vastly different positions. All right, so in science, if we make a claim, we have to back it up with evidence. Here's some of Wegener's evidence for continental drift. One of the first things that got the wheels in his head turning is that some of the continents, if you look at them on the map, it looks like they would fit together like puzzle pieces. The most obvious is South America and Africa. Indeed, most students, sometime in school, they see a globe or a map, and they notice this right away. I remember noticing this probably in about third grade before I ever heard anything about continental drift or plate tectonics. And I think most students tend to notice this. It's just that's one of the most obvious two continents that look like they fit together. Now, something that's really important to note is that if we could readily see the continental shelves, you would notice that these continents fit together even better than they appear to at first glance. All right, furthermore, Fossils of plants and animals of the same species that are now extinct can be found on different continents. And earlier, before Wegener came about with his ideas, there were other explanations. Some of them were that some of these animals could swim, and that's how, they existed on different continents. That was not a very strong idea. Another one was that they were land bridges between the continents that over time eroded away. That idea was a little bit better, but still not quite as sound as Wegener's idea that the continents had moved over time. Also, from continent to continent, there are very similar rock layers. Okay, if you look at the order of the rock layers in South America, Africa, India, Antarctica, and Australia, you can see some very striking similarities. You have the same three layers that occur at all these different places. You have this layer of glacial till, followed by this layer of coal and shale and sandstone, and then topped off with basalt lava flows. All right, so now since the continents are separated by oceans, Wegener's idea about this is that these rock layers all were formed when those continents were still a part of Pangaea. All right, so scientists and other interested individuals agreed that Wegener had some compelling evidence, but they wondered why we could not currently feel the continents moving. Because when you first start to imagine this in your head, us human beings, we only live roughly 80 years if we're lucky. So what can happen over, much more vast periods of time can kind of be lost on us. In the human mind, we think of things happening a little quicker. We think of things happening in our lifetime. We think the movement of the continents should be something we can feel. Now, actually, we can feel the movement of continents from time to time in the form of earthquakes, but that didn't quite register with everybody in the time period we're talking about in the early 1900s. So these people, said, there should be evidence to show that the continents were still moving today if Wegener's hypothesis was correct. And at the time, the evidence just wasn't there. Furthermore, Wegener was a meteorologist. That's what he had studied, and that was his forte. He was not a geologist, but he was here hypothesizing about geology. So more properly trained geologists, they just kind of dismissed him. They said, well, Wegener, he probably doesn't know about this or that, and probably referred to established ideas of the time that maybe have now since been discredited, and used those things to try to discredit Wegener. They just thought that, he's not a geologist. He can't account for everything we can, so he's not that credible of a source. Okay, so most geologists were not ready to take a serious look at what he was saying. Wegener, studying meteorology and climate in Greenland, which, if you know anything about Greenland, is a very snowy, glacier-covered country. Or I should say landmass. It's not its own country. It's actually owned by the country of Denmark. Anyways, Wegener was there. He's studying climate, and he dies there. All right? He doesn't live through one of his expeditions. So in his lifetime, his ideas about the continents moving were never accepted. He dies with most people thinking that he's a kook, or that he doesn't know what he's talking about, or that he's not operating on sound science. The main reason the scientists of Wegener's day had a hard time accepting what he had to say was because there was no apparent mechanism for the movement of the continents. They could not explain what would cause continents to move, and that was a problem. Okay? Maybe there was some evidence the continents had moved, and some scientists were kind of listening to that, but none of them, not even Wegener, had the right idea about what could possibly cause continents to move. So in Wegener's lifetime, His ideas did not really catch on. Fast forward some 30 years or so after Wegener's death, this other scientist, Harry Hess, made a discovery that would make people reassess what Wegener had said. And I know that this says Henry Hess here, but that's a typo. His name was actually Harry Hess. So, using new radar technology, Hess discovered the seafloor has these two really important features, trenches and mid-ocean ridges. Studying these features, he proposed the theory of seafloor spreading. So Hess proposed that beneath the surface of the Earth, there's hot material down under there that is less dense than the material around it. All right, meaning that here again we're going to have convection going on. You're going to have the hotter material in the Earth rising and the cooler material falling. Now, inside the Earth, none of the material is cool. It's all hot, okay? That's why I'm using the relative terms, hotter, cooler. But just keep in mind, it's all hot. Just some areas are hotter and less dense, while other ones are less hot and more dense. So the hotter, more dense material is going to rise, while the less hot, more dense material is going to sink. So Hess hypothesized that the hotter, less dense material is rising toward the surface at the mid-ocean ridges and then flowing sideways, pushing the seafloor away from the ridge in both directions, such as you see in the picture here. You have the magma rising here, and this puts pressure on these two plates right here and pushes them apart. As it does that, some of this magma cools on each side, creating new seafloor. So this process of the magma rising up at the mid-ocean ridges and pushing the plates apart is now known as ridge push. So here Hess is he's kind of starting to put the pieces of the puzzle together. He's starting to solve this mystery of the mechanism that causes the continents to move. So as the seafloor spreads apart at the mid-ocean ridge, new seafloor is created, like I was saying on the last slide. The older seafloor moves away from the ridge in the opposite directions. All right? You have older seafloor going this way and older seafloor going this way. Okay, so the newest seafloor is being created right here where that new magma is cooling into new seafloor. So this theory of seafloor spread and explained how the crust could move. All right, whereas the earlier theory of continental drift, it just said, hey, we think continents move. We don't know how, but we think they move. All right, so now we've got this evidence of seafloor spreading, and this starts to explain the how and why of continental movement. All right, in 1968, scientists aboard the research ship, the Glomar Challenger, began gathering information about the rocks on the seafloor, and they found that the youngest rocks are indeed located right at the mid-ocean ridges. So, in other words, the newest seafloor is right there at the ridge, and as you go away from the ridge in either direction, the seafloor gets progressively older and older. And this is really sound evidence for the idea that magma's rising up at the mid-ocean ridge, pushing the plates apart, and creating new seafloor where some of that magma is cooling and pushing the older seafloor apart. So this further solidified the validity of Hess's evidence, and all of a sudden, Wegener doesn't seem so much like a kook anymore. He's starting to get some vindication. Really, it's too bad he didn't get to live to see that. All right, so seafloor spreading provided insight into the mechanism for how the continents moved. All right. The magma, which pushes up at the mid-ocean ridge, provides a new seafloor that pushes the plates. And then, something we haven't mentioned yet, at subduction zones, which are far away from the mid-ocean ridge, all right, the oldest seafloor is kind of pushed back down into the earth and remelted and kind of recycled into magma again. So the mechanism for plate tectonics, or the movement of the plates on Earth, is convection currents inside the Earth. And you can see this illustrated here in this picture. You have these movements of magma, and they kind of push and pull, and they kind of drag on the plates and cause them to move in various directions depending on the flow of the magma under the surface of the Earth. So both Hess's discovery and Wegener's continental drift theory combined into what scientists now call the theory of plate tectonics, which states that the Earth's crust and part of the upper mantle, in other words, that mechanical layer, the lithosphere, is broken up into sections called plates, which move on a plastic-like layer of the mantle that we call the asthenosphere. Alright, so the theory of plate tectonics explains the cause of the movement of the continents, of course, but also it explains why we experience earthquakes, why we have mountains, and why there are volcanoes. And that's something we're going to go more in depth on in future lessons. Here we have just a diagram of the major tectonic plates. You can see that some of them are very, very large, like, say, the North American plate here, which includes all of this and this here. You have the Eurasian plate, very large plate. Other large plates are the Pacific plate, the Antarctic plate, South American plate, Indo-Australian, African. Some of the still major but not quite as large plates are the Philippine plate, Indian plate, Arabian plate, Caribbean plate, Cocos plate, Juan de Fuca plate, Nazca plate, the Scotia plate.